the crest, which will be this, is left, troughs of 0. There's nothing left for this. And that's at the start. Then it explodes. The ends of it explode. So it's this is not a non-starter. This is what you're seeing with the white lines, the two sides, group and phase. So when it comes time to do the relativity, you make a coordinate system like this with 2 CW. The white lines, they're squares. But the pulse lines, the right and left, they're these things. And they make squares, and this is what we're looking at before. See if I can, there's a Bohr web simulation, but there also was I had put a link on this one to go Pirelli.
It's somewhere in there.
There used to be a little
I
thing
might have
down there.
overwritten it in my haste to get into class.
Oh, here we go. There it
It's
is.
Not for...
Yeah, you just click on it. It doesn't have the little blue arrow that it should have.
I see,
But
yes.
there are the pulses following the pulse lines. But that's because these pulses, with all their frequencies, you can see the frequencies they have in them, and not only, they're not constant amplitude, they're tapered. When you taper them, you make smooth pulses. They generate squares when they cross each other and actually do some interference, but the rest of it's classical Newton-like motion for that. And that will appear, and I'll just go ahead and leave that one and come back and get another one. I'm going to go back to the original guy here.
And since you're on your air, you might as well kill some of those windows.
Yeah,
They're
that's
hogging
got so
resources.
many of them.
Courtney disaster.
Yeah. See if I can find the other window here. This is Fourier lecture 13. That's what we want. I don't see what it is I'm looking for.
Oh, you switched files. You're in the lecture 13
Yeah.
and no longer in 12.5.
Yeah, that's what I've got to do. I've got to go find 12.5.
There we go.
Okay. Going forward with that is this thing right here. And here's what the pulse waves look like with the pulses are now this guy, that's the left, and then the right is this guy right there that makes these paths, and this one makes that path right there. And so I'll see if I can get that one going using our old Pirelli site.
Well, you got to use the link down below.
Oh, see,
That's right. You had it. There it is.
that's the new one.
It's hidden behind there somewhere. Just hit it.
Let's see what happens. This is the new one. But anyway, this has a pulse coming through that goes on that path, and then a whole bunch of high frequency pulses associated with these guys here going the other way. So that produces the framework for the Minkowski graph, the right and left framework for a Minkowski graph. And since the pulses don't explode, they make nice straight paths without any fussing. You see a little bit of the wrinkling that's associated with not quite tapering these things perfectly, but you get the idea from this. So that's I think that's pretty much what we should stop with. But I've left you with this because I would, as long as we're going to be talking about symmetry of waves, it really can't leave out the idea that you make relativity out of these objects. That this is a Minkowski graph, and this is what it would look like if you used the pulses. You make a baseball diamond in space-time when you don't have a Doppler shift and you don't have any velocity relative to the wave cavity. When you do have a really high 3/5 the speed of light velocity, you get this for the space-time graph, and you get this for a sort of Newtonian space-time graph where the rectangles surround two of these objects right here. Two of those rhombuses. Okay, that's a lot of stuff. Any questions about the...
So will we get to, it's probably not today, but will we get to some of the other stuff with the fractal topics?
Some of the other stuff that's on this particular,
Yeah.
such as
Forward circles.
this stuff. This one, you see, I'm sort of leaving you with as an opportunity to go ahead and study relativity from one of our older ways of doing it. But while you're at it, you could take a look at, these are links to the newer papers that, you know,
That one's the older one. It's the larger one.
Yeah, it's older and larger. There's a, when you look on the website at the bottom, you'll see both of them there. They have kind of similar names. We haven't really straightened out what name we're going to use for this.
Mm-hmm.
There's a good chance that this is going to, that this simple stuff with the waves and the relativity, here's the K4, and that's a right-handed moving, K left, which is the infrared laser going to the left, with ultraviolet going that way, and then the group and the phase vectors showing their group being less than the speed of light and a phase being greater than the speed of light. Now we've got space here and time here, unlike the game we were playing over there. And then on this side you see they're flipped. The phase is here and the group is here instead of the other way around in per space time. Anyway, this is probably the old one linked right there. But it's good. I mean, it just takes a little longer to read through it. Then there are the lectures that go with it. This is, you know, putting this thing together to show the half sum and half difference numerically coming out to be the values that are 5/4, 3/4. Remember that when you pick this particular example where you have a Doppler of 2, that means you have a Doppler of 2 and you have a red Doppler of 1/2, reciprocal. So you've got e to the rho plus or minus over 2, e to the minus rho. And what you've got for your diagrams of the triangle are all 3, 4, 5 triangles. This thing makes a 3/4 over 5/4. That's the phase vector right here, 3/4 over 5/4. The group vector is just below it. I think it'll show right there, the new grandstand, G for grandstand, P for pitcher's mound, right? Big deal. Okay, so this one has got 5/4 this way, that's 0.8, and 3/4 this way. They make up the hyperbolic cosine and the hyperbolic sine, which is the basis of the Lorentz relativistic transformation. So basically you get relativity for free by simply looking at two waves interfering with each other. And that's what this geometry over on the side is doing, but it's doing it per space-time, where you can say that you have made a matter wave that has quantum mechanical properties. So we're basically deriving relativity and quantum mechanics just by looking at two waves carefully and their interference properties. And that's what the rest of this lecture is. This is if you click the relativity wave app here, make a liar of myself, I'll see what happens.
Took you to another page.
Yeah. I was expecting something that I could actually move, but that didn't show up, so I'll go back.
Yeah, it shouldn't have done that.
Yeah, that,
Hover over it and you'll perhaps be able to see what the link is, and then we'll
let's see,
get.
yeah, it's hard to get some of this stuff to work sometimes. I'm going to go back to the 13 and go forward from there to, well, it's not the one I want. Let's go here to 12.5 and go back. Yeah, there. So there's. I'm surprised that's not. Oh yes, that's what I'm seeing. Anyway, this is where we were, and I don't know if I can move it that way. Yeah, I can. So that's the thing that's giving you the coordinate system. That's the rhombus right there. That's in these wave graphs. And then this is the thing that I was trying to get, but it doesn't seem to want to come up. This is another thing in that paper that puts the space-time and the per space-time together to get all these numbers that define not just space-time relativity, but also these bizarre, everyone would think they were bizarre. You can see from this that they make sense. It's what waves do. They shrink and slow down and do all kinds of stuff, and hyperbola plays a major role in this. And this is a proof right here. Just go through this little step thing, deriving the MC squared as the bottom of the hyperbola, just based on the fact that these two behave like kinetic energy and momentum. That's this resemble formulas of Newton's kinetic energy and momentum. This is where you make the connection with mechanics and the wave phenomena. And you get both the de Broglie 1921 relationship, which is the momentum is given by that. It's just a hyperbolic sign for the kappa. And then this one right here is hyperbolic cosine for the frequency. That's basically deriving Planck's axiom by doing this. That doesn't happen very often. So, as I said, this looked like lovely coincidences and a cheap trick. It's an expensive trick, and it's natural wave conspiracy. That's what's going on here when you use the exact values from this geometrical table. And the rest of this is just taking it apart. This is something that you can play with. Just grab this thing once it comes up. Let me try and see if that will
I'll
come
put that
up.
one in, it should work.
If it does, we're in pretty good shape. Yeah. So this is grab any one of these and watch the Lagrangian function of group velocity. That's this distance here. That's the Lagrangian. That's the overall phase of a moving mass. Meanwhile, as you go faster and faster, the Hamiltonian grows exponentially with hyperbolic cosine, and the momentum grows exponentially with a hyperbolic sine. But the group velocity is limited by c. So when you get to this point, you're approaching c and you can't go any further. Your Lagrangian is approaching zero, minus a small quantity. And that's, I think, really cool to see all that in one moving diagram. Phase velocity is that distance right there. So all of those trigonometric functions, both the circular trigonometric functions and their equal counterparts, the numbers here, hyperbolic tangent, that matches this ordinary sine. But that means then that the hyperbolic sine matches the ordinary tangent. So you can either work with the logarithm of the Doppler, or you can work with the stellar aberration angle, which is the polar coordinate of the Lagrangian. That sounds crazy, but it's right there. It's basically child's play trigonometry. So that's what the rest of this 12.5 is. I thought you should just have a piece of it to play with, and then use the links to go outside of it.
Yeah,
Okay?
It's much more instructive to be able to go from the white light to the lower mass light plots and see how they differ.
If things go right, this is actually going to be in the Handbook of Physics. Springer Handbook of Physics. I've already got one paper in there, and the guy says I want to, to add some more of the fundamental stuff. So I'm hoping they'll put the electronic version of this so that people can play with this. I mean, look at, here's the Legendre transformation of the Hamiltonian value to the Lagrangian value. That's a big deal, right? And it's just a mystery. When you see it in the classical mechanics book, only the Russian, Landau and Lifshitz, make some sense out of it, but only classically. But here's the idea. You have it happens that the slope of this, which is the group velocity, that slope comes down here through an intersection with another tangent to the value of the Lagrangian. So that's the Legendre transformation. It's taking that slope, following it to the intercept, and the intercept is exactly the minus Lagrangian. And then a tangent goes through the Lagrangian circle, comes back and hits right here, which is the Hamiltonian. So that's the inverse Legendre transformation right there. It's all due to the waves. It's all due to the fact that the phase is kx minus omega t. That's k, which is momentum, times x, times dx, minus the frequency, which is energy, dt. And that's the Poincare differential. And it's the Poincare invariant, because phase is the ultimate dimensionless invariant on which all of physics is based. We're talking about everything that we know in physics is due to that result, that invariance.
Can I think of the phase then as a view into the underlying energy content that I can't see?
You can, in the following sense, that when you talk about the frequency of the L is d overall phase dt, but that phase is proportional to the momentum, and then dx dt, that's the group velocity, minus the Hamiltonian there. Now what you do is you go through and you say d phi, this is the Poincare differential, is equal to p dx minus h dt right here. And you see what you're doing is, once we've proved that the momentum is proportional to k, right, by h bar, okay, so this is k dx minus, and then this thing right here, h, that's h, big H, is little h omega dt. So there's all that advanced classical mechanics hiding in this, but when you see it as a wave, it's just a differential of the phase. So there's the external thing that the particle bulldozes space and time with, that's a sort of a heartbeat that's gotten from, because he's going so fast, his veins are pulsing or something. Anyway, the idea is that that's the thing that determines what that particle is going to do, and it interferes with other waves, you see. That's the sort of an external effect, okay? But inside that, always, will be this frequency right here. That is the heartbeat of that piece of matter. And that's what becomes mc squared, equal to this, differential that. And go back to this one right here. This is the rate of change of the phase. So that's the actual overall phase translating, and then this thing is proportional to the local heartbeat of the wave oscillation. So these are different whenever you're moving. And remember, this thing right here is velocity times time, group velocity times dt. Okay, dx is du. Oh, I'm sorry, u dt. Okay, on this. So the usual way we write up there on the board, this is LDT equal K, I'm sorry, P, the momentum, dx minus the energy, Hamiltonian energy, dt. Okay, so if I divide by dt, I get L equal P dx dt minus H. That's the Legendre transform right there. Okay, this is the Poincare action right there. This is all classical. But then you turn the P into H bar K and the big H into little h omega, and you get this stuff. And it's just child's play. Deriving each one of these takes pages in these stupid classical mechanics books. And that's because you're going backwards. You're not aware that the waves are responsible for all this behavior. And it's light waves. That's what's even more amazing.
Yeah.
Put two light waves together and you get matter. Exact rules for it. And don't embarrass your professors when you get to Princeton. You tell them this, they'll think you're crazy. So if you're really good at explaining it, they won't think that.